Hey everyone, thanks for joining me for this discussion on Python for linear algebra. As a reminder, Python is not a requirement for our course, but I do think it may benefit you in the way of making you more efficient later on in our course. In particular, once you feel comfortable with the row reduction process, once you feel like you can do that by hand and consistently do it well, we can move beyond having to do all that arithmetic and have you use Python so that you can focus on really working with the concepts that we're trying to highlight later on in our course. So again, this discussion is completely optional. Python use is something that's optional. You can use it if you want. You can completely ignore it as well. That's fine. So I've got some warm-up problems as usual in the notebook. We're going to skip over these in this video. I won't address them, but I would encourage you to pause the video for a few minutes and just try one or more of those warm-up problems. Your goal here is to reduce the matrices into their reduced row echelon forms. Again, remember that's the form where I have pivots, and those pivots take on values of 1, and those 1s are the only non-zero entries in their columns. So I have zeros below and above all of those pivot entries. So see what you can do with those. If you have questions on that, please come see me. Let's work together. Again, I've said this a lot and I'll say it some more. Row reduction is a procedure that we're going to leverage throughout our entire semester together. It's something that really we need to get down, and the time you spend here and now will be time well spent later on. You'll really appreciate that you spent the time. All right. So just some reminders and what we're up against today. First, we can rewrite linear systems of equations as matrices, in particular those augmented coefficient matrices. So an m by n system, a system with m equations and n variables, can be encoded by an m by n plus 1 augmented matrix. We're getting the extra column because of the constant vector, the vector of values to the right of those equal signs in the system. Once we have that augmented coefficient matrix, we can use the 3 permissible row reduction operations. Remember, that's scaling. I can multiply any row by a non-zero scalar. Swapping, I can swap the position of 2 rows. Or replacement, I can take a row and I can replace it by a copy of itself plus a scaled copy of another row. This amounts to things like adding 2 equations together in a system, something that you've done prior. The goal of using these row reduction operations is to reduce the matrices to simpler forms that provide us some additional information about the system. So solutions read from a reduced augmented matrix are the same as the solutions read from an original augmented matrix. So we're not changing the solutions to the system by engaging in these row reduction operations, which is extremely important. The 2 forms that we are most interested in are this first one, row echelon form, where I have this staircase format. These black square entries are denoting our pivots. Pivots, remember, are the leftmost non-zero entry in any row. And for us to be in row echelon form, we just need to have pivots, and every entry below a pivot is 0. So we've got this staircase form, and all of the entries below the staircase are zeros. This is going to tell us how many solutions we have, and if we have solutions at all. Remember, if there is a pivot in this rightmost column, there are no solutions to the system. I'd have an equation that says 0 is equal to some non-zero number, which we know is a contradiction and can't happen. So that's what's telling us that there are no solutions in that case. If there is a pivot in every column to the left of this augmenting line, then I have a unique solution. And if there's a column to the left of this augmenting line that doesn't have a pivot, and it's also the case that this rightmost column doesn't have a pivot, Then I have free variables, at least one free variable. And once you have free variables, you have infinitely many solutions. So the row echelon form really does tell you about how many solutions your system has. It doesn't do a great job, though, at telling you what those solutions are. If you were to try to solve a system from its row echelon form, you have a lot of arithmetic still to do. You can use a procedure called back substitution, where you solve the bottom equation for the bottom variable, or for the rightmost variable, the variable corresponding to the column that its pivot is in, and then move back up the system. However, we can pursue a further reduced form for our augmented matrices called reduced row echelon form. In this form, I have the added advantage that all of my pivots take on the value of 1. So those square boxes are no longer anything non-zero. They have to be 1. And those ones, those pivot entries, are the only non-zero entries in their columns. So I have not only zeros below each pivot, but above each pivot. Excuse me, above each pivot as well. From here, excuse me, from here we can read the solutions directly off the reduced row echelon form of the matrix. I'm going to grab a sip of water. All right. So there are two reduced forms for matrices. Again, the leftmost non-zero entries in each row are called pivots. The pivots here can be anything as long as they're non-zero in row echelon form. And in reduced row echelon form, the pivots have to be ones. Again, we talked through how pivots and their locations tell us about the character of the solution space, really about the size of the solution space. Do I have no solutions, one solution, or infinitely many solutions? For today, our focus is just going to be on basic Python for basic calculations with vectors and matrices, as well as row reduction. But don't take this to mean that you can just use Python for everything in our course. You'll still have to show that you can do these arithmetic operations and to do the row reduction operations on gateway exam and in quizzes and exams in class. However, using Python can make you more efficient on homework, and eventually it'll allow me to ask you to do a little bit less row reduction in class. So about Python use, we've covered kind of a lot of this, but Python is a general purpose programming language. That means it's used for a wide range of tasks, anything from website design to app design to game programming and numerical computation as well, which is what we'll use it for here. In MAT350, so in our linear algebra class, we're going to use Python as a tool to help us work more efficiently with objects like vectors and matrices. We've seen in particular that matrix math is tedious, there's lots of steps involved, and lots of opportunity to make mistakes. The computer is really good at making these simple calculations quickly and accurately. Again, just to make this completely explicit, understanding how to row reduce by hand is still an important skill. I'm going to ask you to be able to do it. You'll be required to pass a row reduction gateway exam in this course. After you've done that, after you feel comfortable with row reduction, I'll encourage you to let Python do the heavy lifting for you in terms of row reduction. This is going to free up your brain power to focus on understanding and applying new concepts rather than just spending all your time crunching through row operations and then finding arithmetic mistakes. We don't want to spend all of our time doing those things. So let's get into Python then. We're going to use Python via Google Colab. Google Colab is a service through Google that allows you to run Python directly from your Google Drive without needing to install Python on your machine. This is super convenient because you don't need to manage an environment. You don't need to manage packages or anything. You just go to your Google Drive and everything kind of just works. So in the slide deck, I know in the video you can't click it, but I'll put this link in the description to the video. You'll go to colab.research.google.com while logged into your Google Drive or into your Gmail account. And you can just click this new notebook link. And I'll show you where this new notebook is going to live in your Google Drive. So if you scroll into your Google Drive, you should now that you've gone to that site and created a new notebook, you should now see this gold folder called Colab Notebooks. Any notebook you create this way by going to colab.research.google.com will live inside of here. You can create Colab notebooks in other locations as well. I'm just going to go back to our slide deck so that we can work through more of the slides. All right. So we navigated to that site. We clicked the pop-up to create a new notebook. Now we have a Colab notebook here. For those of you who've used Python before, this is a Jupyter notebook just in your Google Drive. We can click Connect in this top right corner. Connect is going to connect us to a computer that Google owns that has Python installed on it so that we can run Python from Google's computer rather than ours. All right. You can use Python in another environment in this course if you want, but I'm not going to help you troubleshoot those individual environments. So just make sure that you're comfortable with all of the setup and maintenance of your own environment if you do choose to work locally. All right. I'm not going to show you a whole lot about the Jupyter Notebook environment because you're largely going to use these just for calculation, like a calculator space. But Jupyter Notebooks do consist of code cells, that's what I'm seeing here in gray, or text cells, which are in white. You can write freely in the text cells. So my first notebook for MAT350. And then in the code cells, though, you have to write valid Python code. So if you don't write something that's valid, you will get an error. And we'll talk about why that threw an error shortly. And so valid Python code has to go in those code cells. Also, you can run code in a Python code cell by holding down the Shift key and hitting the Enter key, which will run all of the code in that cell. For arithmetic in Python, we can use Python for all the basic mathematical operations: addition, subtraction, multiplication, division. The one that's maybe not the way you would think to write it is multiplication. Exponents. You can't use the caret character. That's a different operation. So to raise a value to a number to a power, you use ** to do that. There is a warning. This is actually the error that I produced for you just a few seconds ago, that if you want to multiply, you have to explicitly use the times operator. Writing something like this, 5 times 8 minus 6, makes total sense mathematically, but Python is not going to interpret that in the way we would want it to. It's going to say, hey, I have a function called 5, and you're trying to plug 8 minus 6 into that function, but I don't recognize a function called 5. And so Python will throw an error. We'll have to write something like, so I'm going to show you the error, 5, 8 minus 6. The spacing is not important here. I will put spaces between addition and subtraction operators, just personal preference, but it's not required. So the integer object is not callable. This is saying I tried to plug 8 minus 6 into a function called 5 or to an integer 5, but I'm not allowed to plug values into integers. If you replace or if you add the asterisk there, the calculation works perfectly. So if you're getting a weird error about integers being non-callable, it's almost always this one that you forgot to include the asterisk. All right, so let's try writing or executing each of these expressions in the Python notebook. I'm going to try to do a side-by-side here just so that we can see everything all at once. Hopefully in the video that doesn't make things too tiny, but I'm going to do split screen. And here we are. All right, so the first thing I want to calculate is 3 plus 18 divided by 7. The big thing you've got to be careful of here is making sure that you have parentheses. So 3 plus 18 divided by 7. As long as I have the parentheses, I'm doing the 3 plus 18 first, then I'm dividing by 7. Next one, 3 plus 4 times 2. 3 plus, I'm going to put an extra line here. It's not necessary to do that, but maybe it helps with readability. Here I've got 3 plus 4 times 2, and I get 11. And then 3 squared to the 4th. 3, I'm going to remember to use the double star operator for raising things to exponents. And I'm going to do that again to get that whole expression raised to the 4th. And I get 65, 61, which seems reasonable. That's 3 to the 8th power. And then 16 over 2 squared. 16 over 2 squared. You get 64. That again seems reasonable. 16 over 2 is 8. 8 squared is 64. And then last one, 2 times 5 plus 3 minus 5 halves. 2, 5 plus 3 minus 5 halves. And there is the integer not callable error again. Hopefully you caught me while I was doing that. I've got to explicitly use the multiplication operator there. And so now I get 13 and a half. You might have been wondering as we went along here why only one number is being printed out. None of these earlier values are being printed. And that's because by default, the Jupyter Notebook environment is just printing out the result of the last expression in the code cell. If we want everything printed out, we can request that explicitly by calling the print function on all of these. So print, and then once more. And then we get all of the values printed out. All right. And I'm just going to label that arithmetic in Python. I'll share the link to this notebook with you all as well as part of the description of the video here. All right, so back to the big slides. Variable assignment. We'll often want to do this just to define a matrix or a vector. We're going to use capital letters to denote matrices in our class. I encourage you to do the same in a Python environment. We'll use lowercase letters to represent vectors. Again, probably the same thing here in Python. But just in general, if you're doing any programming or scientific or numerical computation, variable naming is something you want to pay close attention to. In Python, we store values into variables with the equal sign. The name of the variable goes to the left of the equal sign, and then the value we want to store in the variable goes to the right. So here, x equals 5 assigns the integer 5 to the variable x. My list equals square brackets 1, 4, 9, 16 assigns the list here. So in Python, lists are denoted by square brackets. We're going to make use of square brackets a lot in linear algebra. That's the way we're going to define vectors and also to define matrices. But this will define this list to the variable myList. And Python is going to infer the data type automatically. So if you've done any other programming where you have to initialize a variable and declare its type, that is not something we've got to do here in Python. Naming variables, this is what I want to just mention as something you want to be careful with. In our class, it's not going to matter very much. But again, if you go on to do scientific computing or anything, choosing variable names is an important skill to have. So you want to try to be descriptive. So you'll want to know what you did upon returning to a Python session. What does a variable mean? What does it contain? So using clear, meaningful variable names makes the job that you have in getting back up to speed easier. So a couple of tips and recommendations. Variable names should start with a letter. They can include letters, numbers, and underscores, but no spaces. This is actually a requirement. So you can't start with a number. Special characters sometimes are involved, sometimes are allowed. Spaces are never allowed. Variable names are case sensitive, so height starting with a lowercase h and height starting with a capital H are different variables. Beware of that. Spelling is also important. So if you spell height H-E-I-G-H-T and later on you call height but you do H-I-E-G-H-T, your variable will not be recognized, so check spelling. There are several conventions for typesetting variable names, especially those that are like multiple words. So we have snake case that has underscores between the words, or camel case starts each word with a capital letter. Those are the two most common that I've seen. There are certainly others. My advice to you is to just choose one and stick with it. You want to find a balance between descriptive and concise variable names. So something like EQN1 sol for equation 1 solution is probably a better choice for a variable name than the solution we found for equation 1. You've got to type these variable names over and over and over again. If your variable names are too long, you're going to find that annoying. All right. Okay, so I'm going to just go over to Python quickly and define a couple of objects for us so that we can see how it works. Defining objects in Python. And we're going to do some just basic scalars and lists for now. So my x is 11. If I run that, I have the value 11 stored in a variable called my x. So you'll notice that nothing is printed out when you do that. We do have a green check mark and no error message or warning message underneath it. So Python is indicating to us that it executed everything as expected. But Python is lazy. It's going to do exactly what we ask it to do, nothing more, nothing less. If we asked it to print my x, we get the contents of that variable printed out. We can also print out 2 times my x. We can calculate with these values. We can also define my list. We'll do 1, 2, 4, 9, 16. And then I have my list. Remember, if I'm only trying to print one thing out in a code cell, I don't need print. If I want to be explicit, I can call print. So I've got lists. I'm going to define my second list, or another list. 2, 9, -2, 1, 0. These each have 5 entries in them. And you might expect that I can add my list and another list together, and we can do that. But Python doesn't do what we want it to do. Probably we expected to add 1 and 2 and 2 and 9 and 4 and -2. But all Python did was it took the first list and it added the second list to the back end of the first list. So it smashed those 2 lists together. For that reason, we are not going to want to calculate with lists. Lists are sort of going to be an in-between for us. We're going to need to use something called arrays or matrices or vectors. And we'll import some special functionality for working with that. So beyond base Python, you're essentially working with a calculator for our purposes. But if you want to do anything specialized, you extend Python's functionality by importing modules. We're going to use very few modules in our course. So we're going to, for the most part, make use of the sympy module. This stands for symbolic Python, or symbolic math in Python. This module has functionality for nearly everything we're going to encounter in our course. So we're almost always interested in using sympy. There is another module, though, called numpy, which is numerical Python. That handles matrix and vector operations very well also. We will find use for numpy at locations in our course, in particular when we talk about image compression. When we import modules, so we have to tell Python that we're going to import some extended functionality. We can either load the entire module, like by typing import sympy, or we can import just specific items from that module. So from numpy.linalg, import inv. Inv is a function that will calculate the inverse of a matrix. At this point, after we've imported that functionality, then we can use the inv function. If we import all of sympy, then we have access to all of the functionality in the entire sympy library, or module, whatever you want to call it. All right. So running import sympy will load the sympy module to the current Python session. With sympy imported, we can call and utilize functionality from that module. Anything will be available to us. And the way to do that is to call the module name dot the function that you want to use. So sympy has a matrix function. That matrix function starts with a capital M, but it can be used to define matrices. It is kind of annoying to have to type the entire module name at the beginning of the function name, so we'll often do something called aliasing when we import functionality. That just means we're going to give a different name to the module so that we don't have to type its entire name all the time. So we often will import sympy as SP. This seems to be a very common thing to do. If you Google working with sympy, it's almost always that people are importing sympy this way. The advantage that you get is then you don't have to type sympy.matrix. You get to type sp.matrix instead, which saves you a tiny bit of typing. All right. And here's a use of the sympy matrix function. So I'll use it as well in this notebook. So let's actually define a vector and a matrix. All right. So let's define x. Actually, before we can define xvec, we've got to import sympy as sp. This is going to make sympy functionality available to us. By default, Gemini is enabled here. Gemini is going to prompt you with some code completion. You can turn it off if you want. The way to turn it off is by going over here to Tools, and then Settings, and then AI Assistant, and then Hide Generative AI Features. For our course, I don't think it's going to help you very much to have it enabled. It's going to be more annoying than anything else. So you may actually want to turn it off. Up to you, though. So I'm going to import sympy as sp, and with that imported now, I can define objects. So I'm going to define xvec equals sp dot matrix, and you can see that Gemini is offering, hey, why don't you just use 1, 2, 3? That seems like a reasonable example. I'm going to use 5, -3, 1, 0 for my vector. And then A is going to be a matrix. So I'm following kind of what we're doing in our class. Capital letters are matrices. Lowercase letters are either vectors or scalars. So to make this explicit, I defined xvec to be a vector so that it's clear that it's not a scalar. sp.matrix. And then I'm going to define the one that we have in the slide deck here. One thing that I'm going to do in the notebook that I didn't do in the slide deck is make our job of writing out the matrix a little bit cleaner. So I'm going to hit enter. And now you can see that the matrix itself is going to start with square brackets. And then inside of the matrix, I'm going to define each row as a list inside of square brackets. So I'm going to do 1, 5, 9, 22. And then I'm going to do 0, 2, 17, negative 11. So here's the first row in the matrix, comma, here is the second row in the matrix. So I have right now a 2 by 4 matrix. And if we run that code cell, that executes, and we can print out, maybe we want to tag this with some information. My vector is, I'm actually going to use the code completion there. So my vector is, and then x, my matrix is, and then A. So we can see I've got a vector that's 5, negative 3, 1, 0, and I've got a matrix that's 1, 5, 9, 22 across the first row, 0, 2, 17, negative 11 across the second row. All right. So we can use that matrix function because we've imported sympy. So we've defined this matrix in our notebook. Let me see if you can pause this video and open up a new code cell and use sympy to define this particular matrix. So why don't you pause here, try to define the matrix, and then hit play when you're ready. All right, so hopefully you were able to make that happen, defining the matrix using sympy. I'm going to just add a text cell here indicating what we're doing, define the matrix, and B is what we're defining. So here I've already imported sympy. I don't need to import sympy again. It is available to me. So B is going to be sp.matrix. I'm going to open parentheses to start that function. I'm going to use square brackets to begin the matrix itself. Now each row is going to be a list. I'm going to have negative 2, 8, 5. That's the end of my first row, so I'm going to have a comma. Now my second row, 0, 7, negative 11 halves. Then I'm going to close that row and put a comma. Then 2, 1 half, 5 eighths. That's my third row. I'm going to put a comma. Now my last row, 1 half, comma, negative 4, 6. And there is my matrix. You'll notice this printed out much better than in the previous code cell. I didn't use the print function here. And by default, if you don't use the print function and you just ask for the matrix will be printed out nicely. But if I print explicitly the matrix B, then I'm getting just the text form. So here's the matrix B, and it looks a lot like the matrix that we had set out to define. You'll notice that putting in decimal values here, though, instead of the fractional values. All right. All right. And I'm going to skip over defining the vector, but I'm going to allow you to do that if you want to. The vector here is negative 2, 1, 3 halves. All right. Vector and matrix addition and subtraction. Again, because addition and subtraction are element-wise operations for both vectors and matrices, If you're trying to add two matrices together, then their dimensions must match exactly. That means they have to have the same number of rows as one another and the same number of columns as one another. For vectors, it's the same idea. They have to have the same number of entries as one another. You can think of them as the same number of rows and columns, but vectors will have one column. You can add or subtract matrices or vectors using the regular addition and subtraction signs in Python, as long as they've been defined using sympy. And so let's define a couple of vectors here and add them together. So why don't you give it a shot? And I'm going to add a text cell just to indicate what we're doing. You can pause the video and come back when you're ready. So add two vectors. All right, and hopefully you gave that a shot. I'm going to define here uvec is equal to sp.matrix. This is now my vector 7, 0, negative 2. And then vvec is sp.matrix. And it's got entries 1, negative 3, 4. And now I'm just going to calculate uvec plus vvec. And I get the result. And you can see that it added straight across. 7 plus 1 gave me the 8. 0 plus negative 3 gave me the negative 3. Negative 2 plus 4 gave me the 2. Let's see, again, if we can do something maybe a little bit harder. We're going to compute x minus 2y, where I have these two vectors. Again, hit pause and see if you can do it on your own, and then return here, and I'll do it with you. All right. So here I'm going to define a new xvec. We defined xvec earlier, so when we do this, we're going to be overwriting the original xvec. So that original vector is going to be gone, replaced by this one. So just be wary of that. So I've got a sympy matrix. It's 2, negative 1, 0, 5. And because it's just a vector, I have just the one list, and sympy will interpret that to mean, hey, this is a vector. Now yvec is equal to sp.matrix. And I've got negative 3, 6, 1, negative 2. And because these are compatible, I should be able to add or subtract them. I want to compute this expression over here, x minus 2y. So I've got xvec minus 2 times yvec. And we end up with the result. Again, we had to use that multiplication operator explicitly. If you didn't, then you get an error message. All right. Another example, so compute the matrix sum. Hit pause again, give this a shot, come back, and we'll do it together. All right, so I'm just going to tag this again with an indicator of what we're doing. Add two matrices. We're going to define the matrix A, sp.matrix. Because this is a matrix, it's a little bit easier to read if we split this up over multiple rows when we define it. So 0, 4, negative 2, and then 1, negative 1, 3. And then we can define the matrix B. It's sp.matrix, open parentheses, square brackets, and now 5, negative 4, 2. Then negative 3, 0, 1. I don't know how to turn those tooltips off, sorry, and they do end up being really annoying in the way. But I've got these matrices defined now, and we can then calculate the matrix sum A plus B. All right. So in scalar multiplication, vector addition and subtraction, matrix addition and subtraction weren't operations that were super tedious. They're straightforward. They work the way you would like them to work. And in some sense, they require minimal calculations. But matrix multiplication required many more small operations. It's not an element-wise operation. Let me make this big again so we can see it. Instead, to compute the product matrix A times matrix B, we take dot products between rows of A and columns of B to construct the resulting matrix. This results in a lot of multiplications and additions. It also does require, it puts a mandate on the dimensions of the vectors, the matrices. It requires the number of columns in the matrix A match the number of rows in the matrix B. However, as long as we have that set up, so A is a matrix whose number of columns is the same as the number of rows in the matrix B, then we can do out matrix multiplication. And with sympy, we can just use the times operator. If you're working in numpy, you can't. So you need to use a different operator if you're working in numpy. But for us, we're going to stick to sympy for the majority of our semester together. We'll deal with numpy when we need to, and I'll bring up how to do multiplication when the time arises. So let's see what we can do here. So I've got a few matrices, A and B, a couple of examples. We're going to calculate the matrix products. We're going to see some scenarios where the matrix product is defined and where it is not defined. We're going to see how Python handles those cases. So see if you can define these matrices. So start with 1. See if you can do the matrix multiplication A times B. Then move to 2. Then 3, 4, and 5, doing them one at a time. Before you execute each one, think about whether the matrix multiplication is actually defined, and then see what Python tells you in cases where it's not defined. So hit the pause button, and then come back when you're ready. So again, I'm just going to tag this cell with an indicator of what it is we're doing. We're doing the matrix multiplication. We're going to start by defining the two matrices in part 1. So here A is a sympy matrix. The first row is 1, 0, negative 2. The second row is 3, 1, 1. And then B is another sympy matrix, but this one doesn't have the same dimensions. It is a 3-row by 2-column matrix, so this first row is 1, 4. Second row is 0, negative 2. And third row is 3, 0. The matrix A has 3 columns. The matrix B has 3 rows. So that's a good scenario. We can calculate the product A, B. And so we end up with a 2 by 2 matrix, which is what we expected. The matrix multiplication is done very quickly and accurately, as long as we did all our data entry correctly. So now, same thing, we'll define 2 new matrices. These are the 2 by 2 square matrices. A is sp.matrix. And I've got 3, negative 2, 1, 6. And then B is another sympy matrix. I've got 0, 3. And then the next row, I'm going to get rid of the tooltip. The next row is negative 2, 1, and I can multiply A times B again. And because the number of rows in the first matrix, A, matched the number of columns in the second matrix, the matrix product was defined. We can also do the multiplication in the reverse order here. So we can execute B times A, and we don't get the same thing, which we have come to expect now. We saw that matrix multiplication is not commutative. All right. Let's just do the last 2 really quickly. So we've got another couple of matrices. I've got A is a sympy matrix. It's going to be negative 1, 0 across the first row, and then second row is going to be 3, negative 1. Then the matrix B is going to be across the top row, 1, negative 1, then 2, 0, then -3, 5. And now if I try to do out the multiplication, A times B, the number of columns in the matrix A is 2, but the number of rows in the matrix B is 3. And so when I try to execute this multiplication, those row by column dot products are not going to be defined, and I'm going to get a dimension mismatch. Expecting a list of lists. So I didn't define the matrix correctly. Now that I have defined the matrix correctly, I notice a matrix size mismatch here is the error that's being given to us. So that matrix multiplication is not defined. I'm going to comment it out. That way the code cell doesn't encounter an error. In this environment, as soon as your code cell encounters an error, it aborts executing the code. So commenting that out will allow us to execute now B times A, which should be defined because the number of columns in B is 2 and the number of rows in A is 2. So they match, and I should end up with a 3 by 2 matrix when all is said and done. And so there it is. There's the matrix product B times A. All right. There's one more example. I'm going to skip over it. It's the same thing as the previous examples. The only difference here is that the second object I'm dealing with is a vector, but we've seen that we define vectors the same way as we define matrices, and so you can handle that one. I'm going to skip over also the special vector products. We won't see those again in our course, but for those of you who are taking physics or engineering coursework, you may see the dot product and the cross product show up quite often in your classes. You can calculate dot products and cross products using Python. You define both of your vectors using sympy, and then there's a dot method to calculate dot products and a dot cross method to calculate cross products. All right, and then row reduction. So this is the real reason that we would want to use Python in our course. So I'm just going to tag this Python for row reduction. And then we'll finish out with this one example, and then I think we'll be done with this video. So we'll start by defining this big matrix. A is sp.matrix. This is a large enough matrix that I don't think we'd want to come through and do this by hand. The row reduction by hand anyway. So 3, -2, 0, 1 across the top row. Then 0, 2, 5, -6 along the second row, and then 4, 4, -2, -1 in the third row, and then -2, -3, 0, 9 in the fourth row, and then one more row, 1, 0, 0, -4. Now defining that matrix took more time than the row reduction is going to take. All we've got to do is apply this .rref method to our matrix, and we'll end up with the reduced row echelon form very quickly. And we can see that the reduced row echelon form for this matrix has a row 1, 0, 0, 0, then a second row 0, 1, 0, 0, third row 0, 0, 1, 0, fourth row 0, 0, 0, 1, and a fifth row that's all zeros. And then the last bit here is useful information. This is printing out the pivot columns. So I have a pivot in column 0. Python starts counting from 0, so that's the first column. And then also 1, 2, and 3. So I have a pivot here in every column in this matrix, which is great information, because that will tell us about the number of solutions to the system that this matrix might correspond to if it is an augmented coefficient matrix, or we'll see that pivots in scenarios where I'm just working with a matrix tell us additional information as well. So here it is. Here's how to row reduce in Python. You define the matrix using sympy and then just apply the .rref method to it. Be careful with this. Remember, you're going to have to do row reduction by hand But once you are comfortable and confident with the row reduction process, feel free to switch over to use Python to make yourself more efficient. All right. In the notebook, I've got some examples for you to try. Please take a few minutes and try these out. See if you can solve these systems using Python and row reduction. I'll take a minute with you all and we'll do maybe one of them. We'll do C together, and then I'll let you do the rest. So I'm going to define this matrix just to be C so that it's clear. It's sp.matrix. All right, we're going to define now the rows. There is no way to define an augmented coefficient matrix in SymPy. It's just a matrix. So I've got 1x1, 1x2, 1x3, and then 3 is the constant term. And then in the second row, I've got 2x1s, negative 1x2s, 1x3, and then 1 is the constant. And then in the third row, I've got 1x1, 2x2s, negative 1x3, and then 4 is the constant. And then in this last row, I've got 3x1, 1x2, 2x3, and 7. Now there's my matrix. I'm going to row reduce it by applying the .rref method. So c.rref. This gives me the reduced row echelon form for the matrix, and we can see that there is a pivot again in every column. Since there's a pivot in every column, there must be a pivot in this rightmost column, which means no solutions to that system. All right, see what you can do with A, B, and D, and then also E. I'll see you next time. We've had this conversation about when to use Python. Again, just be honest with yourself. You've got to be able to do row reduction by hand, but once you can, come to Python to increase your efficiency. And then with this, I'm going to skip over the homework because we're already past this discussion, but I'll see you next time. Thanks, everybody.